This is the afternoon session that includes 3 presentations by ECO. So we'll start with an overview of the ECO project. The lecturer is Edouard Audit. So please, Edouard, I think you can start.
Thank you, Lazaros. Okay, you should be able to see the screen now.
Yes, we can see your screen.
Welcome. So, hello again, everyone. So I'm going to present you a brief overview of the EXA2 project, maybe insisting on aspects which are, I would say, most relevant for the joint EXA2PRO-EoCoE workshop. So a few slides of, I would say, background before we go into more technical topics. So ECO is concerned with renewable energy, and you have here some kind of a map of the various sources of energy. So the size of the circle is proportional to the amount of energy. So the little brown dot here, I hope you can see my mouse, is world energy use. So it's about 16 terawatt per year here. The very large yellow or maybe a bit greenish circle is what we receive from the sun. So it's 23,000 in the same unit terawatt per year. So see, extremely large. And then here you have on this arc here what is available from various sources of renewable energy. So tide, geothermal energy, hydro energy, biomass. Here the large green circle is important for us. It's wind for energy. So energy available through wind. And a little here about wave. So you see that wind is a very abundant source of energy. And here you have, I would say, carbonated energy or non-renewable energy, so natural gas, petroleum, uranium, and coal. So as you can see, these will not be able to power us for a very long time, and there is largely enough renewable energy to power the world for a long time and in a sustainable way. So there is this energy transition, so going to renewable energy, and there is also a transition at the same time in the computing world, probably a smaller transition, but still important for us. And there is will be a major change in the next generation of a machine, exascale machine. First of all, they need to have a 100-fold reduction in energy consumption. So that's, I would say, an energy aspect common to both transition. There will be a massive parallelism. You will be able to use several million of computing elements, and probably heterogeneous computing and very deep and structured memory hierarchy will be necessary to achieve exascale. So it means that we will need to have a radical innovation in computing technology, both hardware and software, and of course ECO is more tackling on the software side. Probably something that is not written here is that with this new generation of exascale computer, it will also generate a new usage of HPC, and that will also require for this new usage a new design of code. And among these new usage, probably the use of data and of data analytics coupled to more classical HPC workload will be something very important. And the tools, ECO tools that will be presented this afternoon are very closely linked to that, I would say, data-centric approach. So the main objective of ECO is to use the enormous potential offered by the computing infrastructure to help the energy transition. So to help go to a reliable and low carbon energy supply. And as I just illustrated briefly, ECO is really at the crossroads of both this numerical and energy revolution. And so we are trying to develop an application and propose a new way to develop new application to tackle energy issues. And for now, we are mainly focused on five energy challenge. So wind for energy, meteo for energy, material for energy, water, and fusion. So maybe I can briefly describe them. So wind for energy is really how to optimize wind turbine. So we do both large-scale simulation to optimize the way, for example, wind turbines are placed in a field to optimize their production, taking into account probably complex terrain, the wake of one turbine, how it influences other turbine or windmill and things like that. Meteo for energy is more concerned with a very short weather forecast to assess the production of wind farm and also of solar farm, so large solar panel farm. So these are extremely important to be able to couple efficiently those intermittent source of energy to the grid. So that's on a short time scale, and also on the long run, these simulations are very useful to predict a rare event. I would say very large excess of production, or on the contrary, very low production. And it's also extremely important to be able to quantify this rare event to avoid a full grid breakdown that would, of course, be very damageable. In material for energy domain, we are mainly concerned with solar cells and supercapacitors. So new material either to produce or to store energy. The water for energy actually has two aspects. One is geothermal energy, and the other one is hydropower to assess the resources and how to best manage hydropower resources. And fusion, it's use of simulation to model turbulence in a tokamak, mainly in the framework of the large ITER project. So that is our scientific, applicative scientific challenge. And now the project is organized around 4 exascale, more, of course, it's also science, but more technical challenge that are key issue for the above application. And this challenge are, I will go back in more detail, scalable solver, programming model, I/O and data flow, and ensemble run. So EoCoE is a project, actually it's the second phase. We have the first phase of 3 years, and now we are in the, I would say, roughly at the middle of our second 3-year period. And just to show you the spirit, that was the structure of the first EoCoE1 structure. So the work package where this application, and we have one large work package here, which was gathering all the technical aspects and connecting, I would say, all the pillars together. And in EoCoE2, basically, we made a 90 degrees rotation. And now the work package are the technical challenge. And we have one work package gathering all the science aspects, and the scientific challenge are more orthogonal and using this technical challenge. So I think it's important because, so we did that because we believe now emphasis should be put on a technical aspect to resolve those bottlenecks and to really be organized around those bottlenecks, which are, of course, needed and very useful for EoCoE application, but which can be used for other applications and which are really key issue to tackle exascale application at large and not only for EoCoE applications. Just to emphasize of this exascale endeavor of EoCoE, here you have the management structure, so it's not really the purpose to discuss that here, but just to show you this place, I mean this committee here circled in red, it's the Exascale co-design group. So we have this group, and Paul Gibbons of Julich is the leader of this group, who is really dedicated to organizing the joint co-design of the group. That means making the application and all the work package leader and so technical challenge leader working together in order to ensure a multidisciplinary co-design, and that really the technical challenge deliver into the application. So the role of this co-design, Exascale co-design group is really to monitor application progress toward Exascale, initiate the cooperation between all the work package when really mission critical application design decisions are needed. So really have people discuss together and try to make the best choice for application. And really foster the integrated co-design approach between scientific challenge and a technical work package. So really the goal of this is to make everybody work together for the design of Exascale applications. So just to summarize a bit here, the technical challenges that we are tackling. So the first one is a programming model. So it's concerned with, I would say, HPC performance, scalability, code architecture, and parallelism issue. So really all that to prepare the selected application to the Exascale ecosystem. So it's really, I would say, a high-level approach of code portability and performance, or performance portability. The second one is a scalable solver. So it's really dedicated to a linear algebra solver, and it's designing and implementing a Exascale-enabled linear algebra solver for application. So that's I would say working very well. So you have we have I would say quite a strong team of people who are developing a linear algebra package, and they were in close collaboration with application developer in order to have the best solver for a given application and to tune the solver for a given application. The third technical challenge is the data flow. So it's meant to provide I/O and data flow support for all the scientific challenge, taking into account resiliency, performance, data size, and accessibility. So I will detail that a bit more next. And so within this workshop, most of what we will present is part of this data flow technical challenge. And the last one is an ensemble run. So the goal is to develop Exascale ready framework to build a large ensemble run and in situ data analysis. So it's mainly for one application, which is weather and hydrology. But I think it's also a much broader approach. And I think this ensemble run will be needed and will be a way to use the Exascale system in the future. So all of these technical science tackle really important bottleneck for Exascale application. They are, I say, closely linked to our scientific challenge, but the tools and methodologies that are developed there, and part of them will be presented to you, really have an impact much beyond the code developed in ECO, and really can be used in a wide class of application. So just to illustrate what we're doing in ECO, so we're really we are working on a production application, and we are really trying to improve application, I would say, following the green line. So in this graph, sorry, you have the impact here vertically of the code and HPC readiness. So the impact in the ability of the code to produce a useful science. And here you have, I would say, the HPC readiness. So how close to Exascale is the code, for example. And so one way is to use a mini application. So with mini apps, you can really go fast and scale your code much faster and reach Exascale in the easiest way. But then most of the time you had to get rid of some critical part of the code, and then it's really hard to ramp them back to have a useful application, having impact, and then can be used by scientists. So in ECO, we decided to go along this green line, which means that we are really working on production application and trying to improve it step by step, and always putting back the work we do into the production application, into the which is the main repository of the application, so that the work that we do is directly used by people using the code in production for real-life application. So if you look, oh, this looks a bit strange, but it's okay. So challenge and flagship code. So here you have the technical challenge that I talked to you a few minutes ago, and which are also the work package of the project. And here you have our science challenge. So wind, meteo, material, water, and fusion. And all the bullets here represent a place where you have strong interaction between a technical challenge and a scientific challenge. So, for example, for Alia, you have a strong interaction with programming model and with scalable solver and a bit with the IO work package. For Paflow, you have interaction about everywhere. So this is how the project is built, trying to put these technical advances into production code. And what is important, this production code and this scientific challenge here, so we need to improve the code technically to make them exascale. But of course, it's also extremely important to have a scientific case behind the code. And so in each case, you really have a scientific case that really require exascale. So, I mean, this whole process is supposed to end into doing a good science and important science with a future exascale machine. This is an overview of the project, about the same graph as before, but this time you have all the partners. So we have quite a large number of partners, I think 18 partners in 7 countries. And see, so it's really a collaboration. You don't have one team working on a single system, but it's really a large collaboration with people really interacting and working together. So these are the main objectives as from the description of work. So the first objective of the project is really to produce energy science breakthrough in our 5 key low carbon sector, the one I mentioned. So really, as I said before, to do science and to have codes that have a scientific challenge behind them. Then the second objective is to develop the tools and to have a production-ready HPC software. So I insist again of that we want to improve a production code and not mini apps. Then the third objective is to promote this tool and the methodology and the co-design approach that we are developing. So toward other lab and also industry and SME if possible, which is not always easy. And the last objective that we have is trying to build a community in Europe of, I would say, energy for HPC for energy, sorry. And for that, we have been working a lot with the EERA, so the European Energy Research Alliance, to try to develop an ecosystem around the HPC for energy. I kept this slide about dissemination and communication because as all projects, we have a website, a LinkedIn, and also a YouTube channel, and you might want to look at it. So on our YouTube channel, we have a lot of recorded seminar or webinar, some of them concerning aspects that will be presented today. So you can have a broader view of what we are doing, looking at our YouTube channel. And we also have a newsletter. So if you're interested, you can send your email to Julien, and we will be very happy to forward you our newsletter when the next one is out. We are also implementing a SaaS portal that will be based in Poland and at TSMC. And so far at the beginning, it will be open only to ECO application. And the SaaS portal is really meant to be a showcase of ECO application. But then when times come and when it's well in place and we have more feedback from the first application, we will open the SaaS portal to other applications. And so maybe if you have some showcase using EXA2PRO application, you can use the SaaS portal to showcase this application and try to reach a larger audience. So the idea is to have a simple example that can be put on a web-based approach platform, and then people can see how your codes work, how the application is working, and if they are interested, they can contact you, and then collaboration can be started. So now I will detail a bit the technical challenge, the one which are more related to this workshop. So the programming model technical challenge is mainly concerned with performance evaluation of the code, computational efficiency, portability and flexibility to adapt to future architecture. So this is also directly the goal of EXA2PRO to provide this performance portability. Try to have a separation of concern. So I think Julien will talk a lot about that. So it's really to make sure between the application layer and that with more technical HPC layer are a bit separated, so that the code can be developed on the long run and that everybody can contribute with his own competence. And with basically leveraging the competence of the full community and with improving tools and library. A few examples, I will go quickly on what we are doing. So this is slides, for example, presenting what we have to do to port Alia on GPU. So Alia is a large code of BSC that we are using to model a wind farm. And you see that we have issue with having a GPU execution, CPU execution, and we have issue with linear algebra. So I think even if the approach is a bit different, the problematic and the issue are dealing with are very similar with what was mentioned for EXA2PRO. For ParFlow, it's the same thing. We want to target a GPU, AMR, so it's coupling to a library, and we also have a PDI integration. So PDI is the parallel data interface, which Julien will present just after my presentation. So now the I/O and data flow work package. So the idea is to improve the improvement of I/O accessibility. So really to be able to smoothly support various I/O library and different configuration options of this library. Trying to do that in a smooth way so that the code don't have to be constantly updated, and also to get ready for Exascale, where I/O subsystem will probably be more complex because we probably have a local disk, or maybe not NVRAM, or a local large memory system, and new type of storage. So you need to get ready for that. And so the idea is to have this portable data interface that will be the first eco technology that will be presented, which really meant to be a layer between all these complex application library like POSIX, SDF5, NetCDF, CyanLib, Melissa, and others, and the application. So PDI is meant to make the life much simpler for application developer. So I will go fast here because Julien will present that in detail. So the idea is to have both I/O performance. So you want to be really efficient in writing that. For some application, it can be a bottleneck. So we had some first example of showing a good performance using PDI. You want to have resiliency also. Because on large system, the chance of hardware or software problem is increasing. And so that is more done with FTI. That will be the second technology presented after PDI. So resiliency is also a key issue. And finally, you want to be able to handle extremely large sizes of data. So on this Exascale computer, and even now, actually, you do simulation which have extremely large data set, And to tackle this data set, most of the time it's not possible to write them off disk. So you want to have an in situ visualization or in situ data analysis or data compression to really reduce the overall data footprint. So that's all that these technologies that will be presented in detail in the next presentation. So just to summarize, beyond this technical aspect, so EoCoE is trying to build a hub where HPC and energy community can meet and work for the energy in transition. And really, our goal is to ensure that the energy community can benefit from a common exascale computer. That's why we are developing this application, but also all the tools that we are developing, as I said, have a much broader impact than just the energy application, and so can be used by a much wider community. That's all. Thank you. I will stop here.
Thank you very much, Edouard, for the very informative presentation about EoCoE. Any questions from the participants? Okay, then maybe I have. Please, please, Matt.
Yeah. Hello, can you hear me?
Yes, we can hear you.
Okay, hello. Yes, so hello, Edouard, hello, Lazaros. So, yes, I was part of EoCoE1 and I participated to the building up of EoCoE2. So, and now I'm really interested in so this shift of 90 degrees in the work package. So having technical work package, is it a good move or not, in your opinion? Thanks.
Well, yes, I think it's always the same thing now. People that do, some of the people, not all, that do physics, maybe Herbert, I see him here, can comment on that. They believe that probably there is not enough manpower or enough resources dedicated to a given scientific challenge, for example, to do wind farm modeling. So Herbert is always giving the example of the EXA2PRO project in the US, where there is a huge amount of resources fully dedicated to wind for energy. But overall, I believe it's a good move because I think we are really making important progress on this technical challenge. And I think the next talk of the next two presentations will illustrate that. And at the same time, these, I would say, technical development are really put back into the application and are really useful for the end application, so the wind for energy or the other application. So all in all, yes, I believe it's working quite well.
Okay. Okay, there is one more question by Julien Bigot.
Yep.
Please, Julien.
Yeah, thank you. So Edouard, in your first slide, or maybe the second one, you had a presentation about the amount of resources available. And I was wondering if you have information about the fusion-related resources available, since this is one of the approach taken by the EoCoE project.
Yeah, you meant this slide?
Yeah.
No, I don't have. It's true for so fusion might be in the more distant future, and so I think for fusion, basically you need deuterium. I think you can have most of what you need in seawater if you treat it properly. So I think it would be, it's a very large resources. So it's not renewable per se because you still need some input fuel, but I think it would be a very abundant fuel. So I think it will last for a long time. But I think all this is I mean, it's illustrative, but for example, if you look at the uranium circle here, I think, for example, people who work into nuclear energy would say that with a fast neutron reactor or other kind of breeder, you can have energy for many centuries. Because there, if you divide, it means that less than 50 years, you would not have enough uranium to power nuclear power plant. And I think probably people who work in nuclear energy would not say that. I think the most important point is that if you sufficiently developed renewable energy, in principle, you have enough to provide. I mean, you have enough energy for everyone, I would say. And then you probably have the important problem of intermittency, and so you would need to have a storage and appropriate distribution network to really use efficiently those intermittent sources of energy.
Okay, thank you.
And maybe one final question from my side. I wonder if you consider ARM-based architectures as an underlying platform for the ECO applications. And I mention ARM-based since the EPI, the European Processor Initiative architecture, will be ARM-based. So do you have any plans to evaluate the applications on
yes, very much so. So I didn't present it here, but we have a close collaboration with Riken in Japan, is hosting the Fugaku supercomputer, who is ARM-based. And we are now porting the Gisela code, which is a fusion code. So porting it to the Fugaku computer, so optimizing it for ARM. So it looks simple because ARM is I would say, a simple vector-based processor. But in fact, so I would say just porting the code and having it run on the ARM architecture is very easy. So the entry level is low. But then if you want to have a good performance, it's much more tricky. And Gisela was already a code which was really very well vectorized for the Intel architecture. And if you want to have a good performance on ARM, there's really a lot of work to be done, both on the code and maybe also the compiler are not fully mature yet. And there are maybe some issues there. Yeah, so to answer your question, we are very much working on that. And it's not so easy. You know, everybody say, oh, ARM, no, it's a CPU architecture, so it should be very smooth. And it's probably smoother than some more complex architecture, but it's still a lot of work to have a code really taking full advantage of the ARM vector architecture.
Thank you very much, Edouard.
Thank you, Lazaros.
Okay, so there are no other questions. So, okay, so we can proceed to. Sorry, everything okay? Good. Okay, so I think we can proceed to the next presentation, which is the parallel data interface. The lecturer is Julien Bigot. So, Julien, the floor is yours.
So yes, I'm Julien Bigot, and today I will present the PDI data interface. So as Edouard said, there is a lot of material on the ECO website, including presentations of PDI dedicated for users, how to use it, what is it for, how to use it to do different stuff in your code. So today I will try to instead talk about the architecture of the library. So PDI is a data coupling library, but what does it mean? First, let me start with the reason why we historically first developed PDI. And the reason is related to input-outputs, IOs in the code. When we look at the IO issue, it might look like a simple question, the IO, but in fact, when doing IO, you have to answer a lot of questions. You have a lot of different goals. You want the IO to be easy to use. You want to be efficient, performant, fast. You want the IO library you use to be usable on all the architecture you will use. You want a large language support. You want a lot of things. This is actually a very complex job, and optimizing your I/O is a job on its own. And when you face a problem like that, well, the answer should be, well, it's a complex but common problem. There is a community of dedicated experts. Simple, let's use libraries. So what are the I/O libraries? Well, there are a lot of libraries for I/O in HPC because, as I said, this is a complex problem. And when you want to choose the best library, you have to take a lot of things into account. You have to take into account what type of I/O you want to do. And the type of I/O might be different in different parts of your code. You want to take into account what is the specific execution you're running. At the same code for two different executions, the best I/O library might be different. You want to take into account the specific hardware you're using, because on different hardware, well, the best library might be different. At the end of the day, we can see that there is no one-size-fits-all library. And as a result, we see a lot of codes that end up implementing an I/O abstraction layer in their code to be able to switch libraries. I've worked with multiple codes, and amongst the large-scale HPC codes I've worked with or I've seen, I would say half of them have such an I/O abstraction layer. So this is true for I/O, but if we take a step back and we look at what a code is, HPC code is numerical simulation code. Most of them look somewhat like that. You have first your initialization phase, whatever you do during the initialization. Then you run a main loop, that is your main simulation, and you end up with some kind of finalization. I think I'm not saying something too crazy here. And when we look at the data interaction in such a code, well, there are different kinds of data interaction. At initialization, of course, you might read the parameters of the simulation. You might read some data for initialization. For example, this might be from a previous checkpoint. You might read other data, whatever. Then during the simulation, you might have outputs at each iteration. So you might write intermediate results of the simulation. You might checkpoint your simulation. Maybe you will do some in situ, in transit post-processing. Maybe you want to couple with another code and you self-coupling outputs. You might also have inputs during the simulation. So for example, if you do a data simulation, taking inputs from sensors from the real world, basically, you might have inputs because you're coupled with another code. You might have other kind of inputs during the simulation, and you have other kinds of outputs at the end of the simulation, maybe writing the final results, the final checkpoint, whatever. And what we see is that all of these might seem quite different, but from the code point of view, they are very similar. Basically, from the code point of view, you have your simulation that is running, and you want to import or export data using different kind of libraries. But if you look at it from the simulation, from the numerical simulation point of view, it's really very similar. And that's what we identify as the data coupling problem. And that is the aspect, the question that the PDI library is designed for. So given that, what is the PDI library? So the PDI library is designed to be the glue to come in between parallel, typically MPI numerical simulations and HPC libraries, different HPC libraries, each with its own API. The approach offered by PDI is to say, on the one side, for the code, what we do is we offer a purely declarative API. These are annotations you put in your code that will describe what's happening in your code with no I/O in mind at all. And on the other side, we design a set of plugins, each plugin making it possible to access an existing library. And PDI is what comes in between this annotation library and this plugin system. So how does it work? What is the approach we've taken? Well, the core of PDI is the PDI data store. And the PDI data store, when the codes run and using these annotations, it will store references to the data it generates or the data it will use in this shared PDI data store. Once these references are stored in the data store, PDI emits events that can be handled by the plugins, or the code itself can also emit events using the annotations. When a plugin receives an event, it has an external file where it can read what it should do on each type of event. And typically, it will go get the data it requires from the data store and use it to interact with the HPC library it's dedicated to. So basically, this is really the design of PDI. You have annotations in your code, annotations that make the buffer used in the code available through this data store. And then the plugin reacting to events, either directly sent from the code or sent because new data is available in the data store. The plugins react to these events to handle the data from the data store using the library each plugin is dedicated to. So basically, instead of doing a one step from the code I call the library, it's a two-step process. From the code I write, or as I put references to my data in PDI, and then from the other side, I pull this data and I act with it. This way, the code is completely independent from the libraries on the other side. So, as I said, the core of PDI is this PDI data store. So what is exactly this PDI data store? It's pretty simple. It's just a map of buffer references. So basically it associates a name that acts as the unique identifier of the data to a reference. And what is a PDI reference? Well, it stores multiple information. It stores information about ownership, memory ownership, and locking. So the read-write lock is used to ensure that there is at any time a single writer or multiple readers, so that no two plugins can write the data at the same time, or if the code said using the annotation inform PDI that buffer is available, but it will use it, then no plugin will modify the data while it's used on the user code side. And the memory ownership is used so that the code can say, can get back the total memory ownership when it needs, or it can be a shared memory ownership when it is in the store. We have a concept of strong ownership that you need when you access the data, or what we call semi-weak ownership that can be reclaimed by someone else, and so your reference might be nullified from the outside. A reference is also, so it has this ownership and locking information, but also it contains a type information that gives the memory layout of the data behind the reference and the interpretation of this data. And finally, the last aspect of this reference is, of course, the buffer address. So it's a pointer to the user memory. So you have to realize that when storing a reference to data in the data store, this doesn't incur much overhead, because basically you're only storing a pointer to inside PDI, and so there is no copy that happens in that case. So this is the data store. So basically a mapping between a unique identifier, a name, to a set of references that are designed to make access by multiple independent plugins and the user code possible to the same buffer. This reference include this type information. So what type system, what data model do we support in PDI? Well, basically we support 4 types of data, 4 kinds of types of data. We have scalar data that stores basically a size of the data and an interpretation. Is it an integer, signed or unsigned? Is it a floating point value? Is it a character, etc., etc.? We have an array type. So an array is defined by the size of the array. Padding, we can have padding on both sides for access to sub-arrays, for example, and the type of the elements in the array. There are records. So records is just a list of members where each member has a type and an offset relative to the address of the record itself. And we also support absolute references. So an absolute references, basically it's an address and an address in memory and the type of the data that should be found at the given address. So basically with this data model, we cover the C, the Fortran, also the data model of HDF5, the data model of MPI are all covered by this, MPI data model. And we also support a more, let's say, dynamic version that can be used for Python, for example, for C++, opaque types. So for example, when you have an object and you want to share an object, but you don't know its internal representation, you can still share it with PDI, basically using the same system, but in a much more dynamic version. So all of that is the data in the store is provided through this PDI annotation API that I talked about earlier. And the PDI annotation API is really simple. Basically, it's share and reclaim. These are the main 2 functions of the PDI API, where share means that a buffer in the application is in a coherent, consistent state. So it can be made available to the various PDI plugins. And the result is that it will be referenced in the PDI store. And on the other hand, the reclaim call means that the buffer will now be reused for something else, and that it should be unreferenced from the store because we don't want any plugins to step on our toes while we manipulate the buffers. So really these two are the main two calls you need, and basically only two calls you need to interact with PDI. We also support a notion of event. Basically, you, from the application point of view, you say, okay, I've reached an interesting location in the code. I don't have anything to share, any data associated to it, but still it's an interesting location. So let me notify PDI that I've reached this, this location. So this API is pretty simple. It's available in multiple languages. So this is the C, C++ API, but there is also a Fortran or a Python version of the API. When you use it in the code, it looks like that. So basically, when you use the share and the reclaim calls, in between share and the reclaim that use the same name, the same identifier, you create what we call a shared region in the code, where the data you've shared is made available for the plugins to use. Inside the region, where the user code, the code calling these two functions, should refrain from modifying the data because it's shared with the plugins. And in addition, if you specified PDI in, so you allow the plugin to modify the content of the buffer, well, you should also refrain from accessing the data because a plugin might be in the process of modifying it. So as you can see here, when doing this PDI share, we provide an identifier, the pointer to the data, an information about the access that we give to the plugins, but nothing is said about the type of the data. And the reason for that is because the type is specified in this side file, the YAML file that I talked about earlier. So it's not from the code, but it's in the side file. Actually, you have to specify it for the static languages, those that do not offer a full type introspection API like C, C++, Fortran. For dynamic languages, those that offer this introspection API, there is no need to fully specify the type. Instead, the information is automatically extracted from this. So the type here, you can see that it's specified not directly as a type, but as a template, where instead of direct values, for example, the size of the array, the number of elements in the array should be an integer, but here it uses what we call in PDI a dollar expression. And the dollar expression can reference the value of other data shared to PDI. This makes it possible to write this YAML file once and for all, and to use it in executions where the size of the data or any other aspect of the type changes, as long as you also expose to PDI, as you also share the required information to get the full type. And to do that, PDI distinguishes between two types of data. We have on the one side the pure data, where PDI only keeps a reference, a pointer to the user data. And on the other hand, there is the concept of metadata, where PDI keeps a copy of the user data in order to be able to reuse it even outside of the shared region from the code. This is really useful, especially in that case when you want to reference it elsewhere in the code. So as I said, the type system is based you don't directly express the type, but you express type templates that use these dollar expressions. So what can you do with dollar expression in PDI? What is a dollar expression? Well, the dollar expression is a simple language that supports expression that supports, well, literals, of course. You can say 5, 10, whatever. It supports, as we've seen in the previous slide, references to the store. So in the value of an expression can be the value of something that is inside the store. So if it's a scalar, you just references, but you can also access sub-elements in an array. You can access members of a record, etc., etc. And it also supports operation using the same operators as C. So plus, minus, divide, division, multiplication, etc., etc. And the types supported by dollar expressions are, well, scalars. You can express strings, integers, floating point values, or array, or records. So basically everything you manipulate in PDI, you can express it as a dollar expression. So to summarize what we have inside PDI, let me remind you. We have on the one side this PDI data store that is a map of buffer references. So it associates to a unique identifier, a reference with an address to the data, the type of the data found at this address, and read-write log and ownership information, so that the various plugins and the user code can share the access to the underlying buffer. And PDI also supports elements to make it easy to use from the user point of view with these type templates based on the dollar expressions. So the core of PDI is actually pretty simple, and the way you use it is also very simple. From the code, basically it's just write your code, annotate the buffer that are available, and when they are available using this share reclaim API, compile the code, and from the code point of view, basically that's it. And then on the other side, in the YAML, well, you have to describe the type of the shared data for now. And then you can use our pre-made plugins, or you can actually write your own code to choose what libraries to use. And these plugins, well, they react to events. And when reacting to events, they access the data in the store, and they can use this data to do something. So to do something, what can you do with PDI? What plugins are currently available? Well, this is a subset of the plugins we currently offer. We offer plugins for I/O libraries, so HDF5, NetCDF, ScienLib. We offer plugins for special purpose I/O, let's say, for example, FTI, so for fault tolerance. You will hear more about that in the next talk. Sensei, that is for visualization. So this is a work in progress developed in the framework of the ECO project. There are plugins for integration of your code in a workflow, let's say, coupling with the Dask tool. This is a work in progress. Integration with the FlowVR workflow library, and interaction with the Melissa library developed in the ECO project for ensemble runs. This is also a work in progress in the framework of the ECO project, because Melissa is developed in parallel with the plugin in in PDI. And you can also use plugins that make it possible to run your own code. These plugins can you can use them to execute dollar expression based language, so the language of dollar expression that we've seen earlier. But also you can run very easily Python code or C, C++ Fortran when an event is triggered. I will show a very quick example of how it works with the HDF5 plugin that is called Declarative HDF5, Decla HDF5. This plugin makes it possible to write data in the HDF5 format, or read data actually, and heavily relies on dollar expression and default configuration values to make simple things easy, but complex things possible. So if you just want to write a given variable as HDF5, that is all you have to write, in addition to the information about the types you manipulate in your simulation. You just say, okay, this is the name of the variable I want to write. So main buffer, this is the name of one of the data exposed or shared with PDI, and you give the name of a file, and that's it. Just with that, it will write in a different file using the current iteration ID and the rank, the MPI rank that have been exposed to PDI. At each iteration on each rank, it will write this data to a different file. Or you can do something much more complex by saying, okay, I want to write a given selection. I want to use parallel HDF5. I want to rearrange the data, and I want to get a single array, including all my MPI ranks, including the time dimension, etc. This is also possible with the HDF5 plugin. And compared with a direct use of HDF5, most people tell us that is much easier to use. How does it work inside PDI when you do that? Well, if we look back at our code that we had earlier, and you want to write your data, as I said, to HDF5 file on the disk. So on initialization, the PDI library will be loaded, the store will be created, the file will be loaded, the YAML file will be loaded. In the YAML file, PDI will see that the Decla HDF5 plugin is required, so it will load it. And then the simulation will run. And on each iteration, it will share data reference with PDI. It will store it in the store, and in reaction, the store will emit an event that the HDF5 plugin will receive. And when it does so, it will see from the YAML file that it needs to write this specific data to the disk. So it will go get the data from the store and write it to the disk. So this was the HDF5 plugin. We also support, as I said, executing Python code. So you can just write a bit of Python in your YAML file, and it will be executed on the data that you made available that you shared with PDI, with no need to do anything very complex. The data that you've shared will be made available as NumPy arrays, and you can then re-expose the result of your computation, for example, to let the HDF5 plugin do the writing. This makes it very easy to do stuff like in-process post-processing or data transformation, etc., etc. You can also write, as I said, your own C or C++ or Fortran function. In that case, well, you have to compile the code on the side, but then you can just call your function as you did with the PyCall plugin, and it will run in your simulation process to do post-processing, for example, in the case that the Python code is not efficient enough, or to call libraries where whose API is not covered by a plugin. And in fact, you can also extend PDI by writing a new plugin. It's really easy. A plugin is just one class with a macro, and here it is, you have it. That's the most simple and valid plugin you can write. And then when you have a plugin, you can call the PDI API to register to be notified on the various events. And then you can read your subtree in YAML to know what to do using a very simple API that directly handles the dollar expressions. And you can access the data store as a smart pointers in C++. So it's a pretty easy to write a new plugin. The performance, I will go very quickly because I think that time is running short, but performance basically we've integrated PDI in the Gisela code. That is one of the code of the ECO project. We've compared 3 versions for the checkpointings. One where there is no checkpoint used at all, one where we use HDF5 for checkpointing, one where we use FTI for checkpointing. So all of these were natively implemented in Gisela. And then we compare that with versions that use PDI. And in PDI, either we load no plugin, we load the HDF5 or the FTI plugin, or we load a combination of the two. And we look at the performance. And I will not go into details, but basically what we can see when varying the size of the problem is that the overheads are really negligible. On very low size, there is a bit of noise. So sometimes the PDI version is faster or slower than the native version, but really the overheads are negligible and cannot be seen as soon as we go. It cannot be seen on this figure. The version with or without PDI every time is very close. We've also varied the number of nodes. This is a weak scaling. And here again, we can see that the performance of the version with or without PDI, most of the time we don't see that there are 2 values, and they are very, very similar. However, something that is interesting is that depending on the number of nodes used, the best approach here to do the checkpointing might be different. And the advantage of the PDI approach is that it makes it really easy to switch library and to use the best one when changing the configuration in which you execute. So this was about the performance in terms of execution time. And we have also made evaluation of the memory overhead. And once again, the memory consumption here is very, very similar whether we use PDI or no PDI. So in that case, with no checkpointing, with HDF5, with FTI, in all cases, there is a bit of noise, but in all cases, we see that the memory consumption, depending on the number of instructions executed, is very similar whether you use PDI or not. Okay, one last performance evaluation that was done more recently was to integrate PDI as one of the options for the IOR IO benchmark. And once again, there is always a bit of noise, but once again, we see that the performance are really similar between the 2 approaches, direct IO or IO going through PDI. So to conclude, let me say that PDI is a library that is publicly available. Version 1.0 has just been released. We have packages available. Documentation is available online. This is a very well-tested library. There are a lot of tests executed regularly on the code, daily on the code. And there is a praise training, including information on how to use PDI offered next week for those who are interested. This is really a production level library that is currently integrated in multiple production codes. And let me just say again that PDI is a library for data coupling. It's definitely not an IO library. It just makes IO library available to the codes and supports a clear separation of concerns between the people developing the simulation code and people working on IO optimization with very negligible overhead, especially when compared to the IO time. The current work in progress is to develop more plugins, especially related to coupling issues, so coupling with the Dask data analysis tool, coupling with Melissa developed in the ECO project, coupling with the Sensei in situ analysis, in situ visualization API. And on the other side, we're working to extract the type-related library out of PDI to make it available to others, because we've seen that in many libraries, you have this requirement for a type system, a data model. Usually the data model is read-only. You can describe your type to the library, but not access the information about the type. And we want to make a read-write version available. And we are wondering whether instead of putting this information in the YAML, we could maybe get it from the compiler. So this is one place where there could be maybe a collaboration possible if some of you have similar needs in your libraries. And on that note, let me thank you all. And well, if there are any questions, I can answer them.
Thank you very much, Julien, for the excellent presentations. Is there any question by the presenters? By the, sorry, the participants?
Yes, I'm wondering, so you explained that you annotate the code, but that's like macro and or function call, something like this. And then you have a YAML description on the side. But is it possible to generate the YAML description dynamically? Because I mean, StarPO typically doesn't know what the application wants to do, and it discovers it during the execution. And so we would need to be able to produce the YAML files on the fly.
So currently the YAML file, so in the YAML file, we have two things. One thing is the information about the type of the data. And for this one, as I've been saying here, we're looking to extract it. And we are actually wondering if it's possible to get info from the compiler, because that's the compiler that knows the type of the data best. There is an API to describe the various types, of course. The other thing is in the YAML, we have basically a description of what kind of IO we want to do, or what, this is a plugin specific description. Each plugin receives a subtree of the YAML, and it's the basically where the IO optimizer will write what to do. So currently we don't support providing that through an API because, well, we consider it similar to code, something that the IO optimization specialist will provide. would be really easy to add support for that, but it's not something that was asked by anybody yet.
Any other question?
Mathieu,
yes, please, Matt.
Yes, so thanks for the presentation, Julien. One question about post-processing. So if I want to decouple post-processing from my simulation code, and for example, I would like to use a library like FlowVR that is able to do either in situ or in transit I/O post-processing. Do I need to write a PDI plugin, and that will be used and will be triggered by FlowVR, for example? Or do I need to stick to a kind of FlowVR implementation of my post-processing?
You can mix and match. If you have existing FlowVR post-processing modules, of course you can use them. And you can, if your code is annotated with PDI, you can use it as a FlowVR module. So my advice would be, well, if you have existing modules, just use them as is. But for your next code, because maybe FlowVR is what you want to use right now, but Dask is really more and more interesting alternative, even if it's used in a different way. If you use PDI, then you can switch from one to the other. So my advice, but of course I'm the PDI developer, would be for the code you now develop, it might be better to use PDI. Actually, in the case of Barflow, when talking and developing with Bruno Raffin, who is the developer of Barflow, he kind of agrees with that because Barflow offer, I say Barflow, I mean FlowVR. FlowVR offers a low-level API. Basically, it only receives pointers with no information about the underlying type. So using PDI, you get even a higher level API with type information that you don't have when using raw FlowVR.
Okay, so but then so I understand that if I write a PDI plugin, FlowVR will be able to trigger it.
No, just the code annotated with PDI. No need to do a plugin. Sorry. Plugin, there is one plugin that is already there to basically make your PDI annotated code, make it possible to use it as a FlowVR module. So no need to write a new plugin, just write your code, annotate with PDI, and now just write the correct YAML and it's a potential FlowVR module.
Even better. Okay, thanks.
Okay, any other question? I think one question by Leonardo. Please,
yeah.
Leonardo.
Yes, very quick. Can you hear me?
Yes, we can hear you.
Yeah, just curious, Julien, when working with different applications you have worked, how often do you see the need or to use the event call from PDI? Is this something that is often needed by different applications, and in which context?
It's quite typical, basically. Very often, so I've only shown here the base API, but we have other API that make it possible, for example, to combine a share and a reclaim together with also an event. And very often what we see is applications at a given point have not one, but multiple buffers available. And if you only react to the presence of one of these buffers, it's pretty difficult to know if the others are there or which one will be shared first. So here it's a nice approach to use events to say, okay, I reached this point where all my buffers are available together in a coherent state. So this is the typical use case for the event approach.
Thanks.
Thank you very much, Julien.
Thank you.
So now we will stop for a 30 minutes break and we'll be back at 3:45 for the last presentation. Welcome back to the EXA2PRO workshop for the last presentation titled FTI State-of-the-Art Multi-Level Checkpointing Library by Leonardo Bautista Gomez from BSc. Hello, Leonardo.
Hi.
Can you share your screen?
Yes. Okay.
Okay, great. The floor is yours.
Okay, great. Thank you very much. Okay, so let's start. Thank you all for attending this talk. My name is Leonardo Bautista Gomez. I'm a senior researcher at the Barcelona Super-Computing Center. And I'm going to present this library for multi-level checkpointing. It's called FTI. So let's just start with the why FTI, or why do we need FTI? You know, supercomputers, of course, are growing exponentially. This has been the trend for quite some time. And so, and we expect this to continue for a few more years. And then as the size of the supercomputers grow, the number of components in those machines also grow. And when the number of components grow, the probability of any of those components failing at any time increases, because when you have more components, then more things can go wrong, right? So as you increase the number of components in these systems, failures become more frequent. And in particular, what we call the mean time between failures decreases, meaning that since the probability of something failing in the system increases, then you will see these things happening more frequently. Now, the part of supercomputers that grow exponentially is mostly the compute time, not the compute time, the compute part of the system. So the computing nodes, the processors, and all this part of the system that does the computing. However, the part of the system that is in charge of I/O is not growing exponentially, it's actually growing linearly. So there is a difference between how fast processors evolve versus how fast hard disk evolve, right? And this is making a gap between those two parts of the system. And this creates a bottleneck, what we call usually the I/O bottleneck. So computing is very fast in supercomputers, but then if you really have to write a huge amount of data into the file system, then this might become a bottleneck at some point. And in particular, you have to do this very often, then your code starts to slow down. So to give you an example, imagine you have a system, a petascale system, that has a mean time between failures of about 6 hours, meaning that you have between, you know, it's a system with thousands of computing nodes. And every day you have between, I don't know, 3 to 4 node failures in your system. 3 or 4 failures per day among thousands of computing nodes is not really much. It's a quite highly reliable system, but this is still significant. And then you need to do something when you have a failure, right? Because if you have an application that is running for many, many hours, sometimes days, you don't want to start from scratch when something goes wrong, right? So we do basically the same thing that we do with video games. We checkpoint the progress that we have done so far, so that if you die, killing the big boss, then you would just start from the last part, and you don't have to re-execute the whole game again. You don't have to execute the whole simulation. You would just execute the last segment, right? And then you have to choose a checkpoint interval that is reasonable. If you chose the checkpoint interval too short, then you will spend too much time doing checkpoints. But if the checkpoint interval is too long, then when you have a failure, you will have to re-execute a lot of things. So there is a trade-off there. There is a sweet spot that is when you choose the checkpoint interval. Now let's imagine, just to give an example, hypothetically speaking, that you want to checkpoint an application that is running on 1,000 nodes, and you have about 100 gigabytes of memory per node. This is what you have to checkpoint from each node. Now imagine your file system can tolerate, has a bandwidth of about 100 gigabytes per second. So if you have to move all this data from the compute nodes, 100,000 gigabytes to the file system, and you only have 100 gigabytes per second, then it will take you 1,000 seconds to do this checkpoint. 1,000 seconds is more or less 17 minutes. And if you have to do this, for example, every 2 hours, then you are spending 15% of your time checkpointing. If you do this every hour, then you would spend more or less a third of your time doing checkpointing. And this is still important because if you don't do it, then you will waste more time doing re-executions. So accessing the file system for every checkpoint is very expensive. So this is why we propose multi-level checkpointing. And in particular, in this talk, I'm going to present FTI, the library that we are developing, or that we have been developing for the last 10 years, that offers multi-level checkpointing. Just a reminder, this is supposed to be dynamic, so feel free to raise your hand or ask questions at any time during the talk. So I'm going to give a very brief example of how to use FTI so that you have an idea about what I'm talking about. So let's look about this code. This code, it has an MPI initialization, and then you have an MPI communicator, and then you have a main loop in which you do work. Okay, it has a grid and ghost regions. Imagine this is, for example, a two-dimensional stencil computation. And then at some point, when you reach some accuracy, you finish the execution, and that's it. Then you finalize. It's a very, very simple example. Of course, there is a bunch of things that I removed from the code, but let's just focus on the main thing here. Now, if you want to use FTI inside such a code, there are a couple of things you have to do. First, you have to initialize FTI. For this, you pass two parameters. One is the configuration file, conf.fti, that I'm going to present in a minute. And then you pass the MPI conword. And then at the end, you give finalize, right? Then you have to give a number of variables, or you have to say to FTI which are the variables that you want to protect in your checkpoint. So for example, here we are going to checkpoint the loop counter step. We're going to checkpoint the two-dimensional grid that is called grid. So we pass the pointer. And let's imagine for some reason, we also need to checkpoint the ghost regions. It's not always the case, but just for this example, let's imagine we have to do that. So we pass this third parameter. So this is saying to FTI, well, these are the 3 pointers that I want you to checkpoint when you checkpoint. And if you save this, I can restart from it. This is all I need. All the rest of variables are temporary. I can recreate the data if there is a failure. And there's one last thing that you have to do is inside the main loop, you place an FTI snapshot. And that's it. That's pretty much all you need to do to checkpoint with FTI. Now, from the configuration file, what we need to see? What we need to see is the node size is just basically saying to FTI how many processes are running in each node. Then you give the checkpoint directory. In this case, we assume you have, for example, SSDs on the compute nodes. Now you have non-volatile memories. You also have burst buffers. There are a wide set of technologies where you can stock things in local, not in the file system. Then global there is you pass the parallel file system path where you want to write your checkpoints. And then we also have a metadata directory. And then you say to FTI when you want, at which frequency you want to checkpoint. For example, here is every 2 hours, so 120 minutes, I want to checkpoint in level 4. Level 4 is in the file system. So this is basically the same I was doing before. Now, if I want to change this to multi-level checkpointing, I just need to change the configuration file. I didn't need to change anything inside the code. Just in the configuration file, I say, well, now you checkpoint every 30 minutes in level 1 in my solid state drive, which is much faster than writing in the file system. And then every 6 hours, instead of 2, I can write in the file system, all right? I can also use the level 2. Level 2 is I write my checkpoint in local, but in addition to that, I make a copy of my checkpoint on a neighbor, all right? So that if my node goes down, I have the copy of my checkpoint in a neighbor, all right? So that is level 2. So, and then I play with these different levels of checkpointing to have something that is performant and is still very reliable, right? You will notice also that here I changed from the configuration file, from configuration file to the argument so that I can pass different configuration files to different executions. And still, I don't have to change the source code of the application. So I can launch a simulation with checkpointing with level 1, another one with level 2, another one with a combination, and so on and so on. Now, one of the things that we did was to add Reed-Solomon encoding. The idea is to be more space efficient than data replication. So partner copy is good, but it's still very space consuming. If you want to tolerate multiple failures, like 2 nodes, consecutive nodes failing, you will need to replicate 3 times. And then this becomes very quickly very space consuming. So instead of that, we use erasure codes. And in particular, we use Reed-Solomon encoding for that. And then we use pretty much the same amount of replication of space that partner copy, but we now allow a much, much higher resiliency. And when I say much higher, I mean orders of magnitude higher resiliency than using partner copy. Of course, this is a little bit expensive in terms of computation, but the outcome is very good. So we developed this, we demonstrated that by doing this with Solomon in parallel in subgroups inside the entire simulation, we managed to keep a constant time for the encoding and decoding of these checkpoints. So we published this, as you can see in the bottom, this paper in CCGrid about 10 years ago, more than 10 years ago. And so this allows us to add this level 3 that you see here in the configuration file. So now we have really different levels of reliability from level 1 to level 4, level 4 being the more resilient and level 1 being the less resilient. But we also have different performance, level 1 being the most performance, so the fastest one, and level 4 being the slowest one. So you have this trade-off, and then you can play with these different levels as you wish, and you don't have to change anything in the configuration file. You can just play with, anything in the source code, you can just change the configuration file. One thing that also did is, for example, FTI snapshot basically will just take the snapshot at every 30 minutes, for example, or 60 minutes. And FTI has some timers inside to figure this out. It's more complex than that, but I'm not going to get into the details. But for example, there are some applications that also want to say, I don't know, I'm doing climate simulations and I want to checkpoint at the end of every simulated day, for example. So this is a specific point, and it's not in terms of minutes, but a specific point in my execution. So FTI also allows that using the FTI checkpoint. And then here, basically what you give here in the configuration file is not even used, because you focus only on the code here. And then you can say at which level you want to checkpoint and the ID that you want to give to the checkpoint that you are taking. All right. So one more thing that we did and is to offer asynchronous checkpointing. Asynchronous checkpointing is we call one more thread per node, one more MPI process per node to dedicate it for fault tolerance. And this is extremely useful in heterogeneous systems. For example, when you have, as you can see here in the example, 3 GPUs, and then you have quite a number of cores, CPU cores, but you don't use them because your application is mostly using the GPUs and not the CPUs. Then you can use an extra MPI process in every node to do fault tolerance work. For example, the Reed-Solomon encoding here, the red part. So if you imagine blue is the application execution, yellow is the checkpoint in local, and then red is the asynchronous, is the Reed-Solomon encoding. If you give this work of the Reed-Solomon encoding to the FT dedicated process, then you just need to stop for the time to make the local checkpoint, and that's it. So you have much lower overhead. And as you can see, we did some simulations with number of GPUs going from 300 to over 1,000. And we compute the number of teraflops, so higher is better. And we can see here, the blue line is no checkpointing. The yellow and green line is checkpointing with FTI at different levels. And then the purple or dark red line is a checkpointing into the file system. And this was published again in 2011 here in this paper. You can see the code of FTI here. I also posted it before. And so what happens now is that in the configuration file, you have this head equals 0. So this means that there is no asynchronous, there is no FT or fault tolerance dedicated process. But if you put this to 1 and then you switch from 4 node size to 5, okay, so it means you are, for example, you have 4 GPUs and then 1 extra process to do FTI related work. And then everything that is encoding or transferred to the file system, all these things can happen in parallel as the application is being executed on the GPUs. Now, we also did some work more specifically about GPUs and heterogeneous computing. Now that 8 of the 10 fastest supercomputers are using GPUs. At least that was when I made the slide. Probably that changed in the last version of the list. But anyway, it's quite relevant still. So the thing is that we have several types of memory when we work with heterogeneous systems. We have the host memory, the DRAM. We have the device memory, the GPU. And now we also have the UVM, the Universal United Virtual Memory, right? Unified Virtual Memory. So this is a little bit harder because then when you checkpoint, you don't know exactly where is your data set. Is it in the host? Is it in the device? Where should I go and search for it, right? And so in FTI, we made some work so that basically this becomes absolutely transparent. FTI is capable of understanding where are data sets, where they need to be checkpointed, and does this all in a completely transparent fashion for the user. In addition of that, we use streams and pipelines so that we optimize all data movements. So at the same time, we are transferring data from the GPU to the host when necessary. We are also writing from the host into the SSD, for example, in local. And we are at the same time writing from the SSD to the file system if that is necessary. So we have all these streams and this is completely optimized so that we reduce the checkpoint and recovery cost by 15 and 5 times accordingly. To give an example, imagine this is your code, okay? And so here I have added the allocation memory for the grid and the ghost regions. So you have your mallocs here, and you have your function do work. If you were to pass this to a GPU code, because now you bought a machine with GPUs, the only thing you have to do is to change the mallocs to CUDA malloc, and instead of calling your CPU-based compute work, you call your CUDA kernel. You can call it as you want. But what is important in this slide, and I want you to notice, is that you do not need to change absolutely anything from the FTI perspective. All the calls to FTI remain exactly the same, and all the variables are going to be checkpointed in the same way as if you were executing a CPU, 100% CPU code. All right. So this is what I think I wanted to show on this. Now, we also developed differential checkpointing. For differential checkpointing, the idea is that between one checkpoint and the next, maybe not the entire data set changed, but only part of the data set changed, right? And this is for many reasons the case in many applications. I'm going to explain a few of them here. Now, some people are saying, have studied how to do this using the dirty page technology in the system. Dirty page is every time you use a memory page, if you use it, then you set a bit to say the page is dirty. If the page is dirty, is not dirty, then the this bit is set to 0. So with this, one could say, okay, this memory page has changed, then I have to checkpoint it. If it has not changed, I don't have to checkpoint it. Now this is good, but this is not enough. The reason why this is not enough is because many applications are basically always writing the entire data set, whether there are numerical values that have changed or not. To give you an example, if you are simulating a hurricane, there are regions in the corners of your area, the domain, where maybe the velocity of the wind is 0. Just to give an example, it can be any other type of, but there are some regions where the values are 0. And even through the simulation keeps evolving, those values still and remain 0. But every time, every iteration, you are gonna go and rewrite 0 and 0 and 0. And every time you keep rewriting, from the system perspective, from the operating system perspective, those memory pages did change. But in reality, the value did not change, okay? So the operating system perspective is not enough in order to really catch what has changed or not in the application. So we use a different approach. We use a checksum-based calculation in order to really detect what has changed. And we use blocks of data. And so we divide the checkpoint data in blocks. And then we compute a checksum in that block. And then we see whether something has really changed or not. Again, of course, the size of the block is quite important. If the blocks are too big, then you will have changes all the time. Because even if a little thing, only one line change in the block, you have to take into account the whole block. And if the blocks are too small, then you will spend a lot of time doing checksums. So there is a trade-off. If you want to look at the details, please go and look at the paper that is here in the bottom, specifically 2019. But anyway, what is interesting then is that we managed to implement this differential checkpointing, and we tested with 3 different applications. One is XPeak, heat distribution, and Lulish. And so in the figures that you see here, you see really different ways applications behave when you try differential checkpointing. So to give you an example, so here we have in the x-axis is the ranks from the application. And the y-axis here is how much of this rank has changed. Black being what changed and white what did not change, all right? And then we show this at every 1,000 iterations from 1,000, 2,000, 3,000, 4,000. So what we can see here is for the XPeak application, basically all the ranks have the same amount of changes. And this actually continues completely constant from time to time, from iteration 1,000 to iteration 4,000, it's always the same. Now, the reason for this is because XPeak application is about particles movement. So there are 3 components that always change, is position, velocity, and force. These 3 vectors pretty much all the time are changing. But then you have other components, which is density, mass, and I don't remember exactly what else, that never change because the particles themselves do not change in size, volume, density, or anything like that. So there are 50% of the data that is never changing, right? And this is for all applications. And so this is very constant, this is very static, and this is very simple to take advantage of a differential checkpointing for an application like this. Then we have this heat distribution in the middle that says, well, you know, there is a distribution. You imagine a room and you have a window and you want to see how the temperature changes when you open the window, right? And so the ranks that have data next to the window are going to see changes, but the ones that are in the back will not see changes, right? And so this is why you see these kind of stripes here. So there are some ranks that see a lot of changes, and there are some ranks that don't see any change because they are in the back of the room, right? So depending on the configuration of what you are trying to simulate, you will see this kind of pattern, okay? And this more or less stays the same because the evolution is very slow. So you can see that it actually increases from iteration 2,500 to iteration 10,000. It slowly increases the number of ranks that will see differences, but it takes some time. It takes quite some time. And then for Lulesh, it's even more interesting because it's even more dynamic. Lulesh is a kind of blast simulation. It's a kind of explosion from the center to the borders of the domain. And this is a three-dimensional simulation. So at the beginning, you see that pretty much no rank see any difference. So everything remains the same. So pretty much the second checkpoint that you will do at, for example, at iteration 5000 will be only 1% of the data, that because you don't have to change anything. Is the previous checkpoint is almost as good as the second one, right? And then as the explosion expands, then you will see that more ranks start to see differences, and the amount of changes that change, the amount of data that change for each one of those ranks also increases. So you can see this gradual increase in turbulence that is observable in this differential checkpointing. All right. If you want to see the details again, check the paper. Now, what do you need to do, going back to our example, in order to benefit from differential checkpointing? Do I need to change anything in the source code? Do I need to do anything specific? The answer is no. Basically, just take the configuration file. So here we have a new line that is called differential checkpointing level 4. And then we have another couple of options for differential checkpointing: the mode, the block size. So the block size is already given by default with FTI. And you want to say, yes, I want to enable differential checkpoint. So this is going to become this. So I enable this, the block size is given by default. And then here you give the frequency. For example, now before I was checkpointing every hour with level 4. Now I use differential checkpoint every hour. And then, for example, every 4 hours, I do a complete checkpoint, a complete level 4 checkpoint. So 1 out of 4 is going to be a complete checkpoint. I don't want to compute differences. I want to rewrite the entire thing from scratch. All right. So you can play with these frequencies like that, and you don't need to change absolutely anything inside your source code. Now, there are a couple of I/O features that we also developed. For example, instead, when we do the checkpoints with FTI, we usually use POSIX for the local files. But we can also use MPI/IO. For example, when you are writing to the file system, we can do it with MPI/IO, and you just need to pass this parameter in the configuration file, and that's it. We also have a format, it's a FTI file format. We call it FFF. This is for differential checkpointing. We have two versions of differential checkpointing. This is the first one, and there's a second one. We are also capable of using the Sion-lib library developed at Julien. And we can also produce checkpoint files in HDF5 format in case you want to open your checkpoint files for post-processing or any other reason. And we also have integrated the IME native interface for improving the performance in those systems. We have a couple of other options. For example, keep last checkpoint. This is useful when you want to say, the last checkpoint I do is not because I finished the simulation, is because I have to stop the simulation because the scheduler is going to kill my application, and I'm going to continue tomorrow. So I don't want FTI to clean up all the checkpoints, because then I have to start from scratch. So just keep my last checkpoint, and I'm going to restart from there tomorrow. We can also keep all the level 4 checkpoints in case you need them for specific reasons like post-processing or visualization or whatever. Now, we did another work, which was try to develop Pragma interface. And this is actually, this goes beyond FTI, because the idea is to have an interface that is capable of using multi-level checkpointing libraries. So, for example, FTI, or also Scalable Checkpoint Restart from Lawrence Livermore Laboratory, or the Veloce library developed at Argonne National Laboratory. And so with this Pragma interface, you can basically just plug any of those libraries, and you don't have to change anything inside the source code, right? Basically, we use a Pragma checkpoint interface with 4 options. Here is init, load, store, and shut down. And so with this, we reduce the number of lines of code for the checkpoint part by 71%, 94%, and 64% for FTI, SCR, and Veloce. All right. This is focusing only on the resilience kind of code, right? Where we didn't decrease the application code by 94. That would be kind of weird. And there is, of course, no overhead because we are just translating, you know, the processor, the compiler, the Mercurium compiler that we developed at Barcelona Super-Computing Center is transforming the code into the native library. And, you know, you have different libraries. And this is very useful, for example, if you want the same code to be used in multiple machines, but you don't have all those libraries on those machines. So you can use, with the same code, you can run it in this machine with FTI and another machine with SCR. We did try with a bunch of applications that you can see here, OpenCHK with FTI, with SCR, and with Veloce. And most of the time you have the overhead is always around 1. And so basically, for example, this is the highest overhead, which is 1%, okay, 1.6%, is really negligible, right? We published this in this journal. So if you want details, please look at here. So how does this look? If we come back to our example, if we look from this code, how would this translate to the Pragma interface? Well, it's rather simple. So as I say, we have the Pragma checkpoint init, and we pass the communicator, Pragma checkpoint load, and then we pass the variables that we protect, step, grid, and ghost. And then we have the Pragma checkpoint store, and then here we pass the ID and the level, for example. The level is not always used. It is used in the case of FTI and I think Veloce as well, but SCR does not need this, I think. And then Pragma checkpoint shutdown. So it's really simple. And then with this, you can plug any of those 3 libraries. All right. Elastic recovery. This is some quite recent work that we published in HIPC a couple of months ago. And the idea was to enable applications to restart with a different number of processes versus the initial number of processes they started running, right? So for example, you have an application that is capable of starting the run with, I don't know, 50 processes. And then you say, okay, I'm fine with running with 40 processes. Because, for example, you had a failure and then the machine is full and you can only use 40 or 45, whatever. And then you can say, okay, I want to run with 45, but from the last checkpoint that was taken when I was running 50 processes. So this is something we implemented. We implemented with HDF5. And what we did is, instead of using end-to-end checkpointing, end-to-end meaning every MPI process does one checkpoint file, creates one checkpoint file. Instead of doing that, what we do is that all the processes work together to create one single checkpoint file with a specific structure inside that will be usable no matter how many processes you restart with. Okay, and in addition of doing that, which was actually already implemented by some libraries, we did also kind of a staging approach in which we first checkpoint in local SSD or non-volatile memory or whatever you have in your system using the end-to-end approach, which is very, very fast. But then in the background, using asynchronous checkpointing, as I explained previously, we can aggregate those local checkpoint files into the one master checkpoint file that will be used for elastic restart. We compare this with Adios, and we got a 5x speedup. And so it depends on the application itself, how easy it is to implement this. For regular applications, like heat distribution is really straightforward to create this master checkpoint file, this N2-1 checkpoint. But for irregular applications like XPIC, is a little bit more complex. Because of course, FTI does not know what the application is doing. So the user needs to give some hints on how you want to write those checkpoint files in order for the data to be coherent. And this, again, can be more or less complete depending of how regular is your application. So we evaluated this into, depending on, for different applications, and depending on the amount of checkpoint data that you want to write, and we estimate the relative overhead. As you can see here, with using asynchronous checkpointing, the overhead, I think, goes from 0.2 to 1.5, I think. Is relatively low. And then here we did the same number of processes. We scale from, I don't know, 100 processes to 6,000 processes, more or less. We can see that pretty much the line is flat. And so we can expect that as we go to thousands, tens of thousands of processes, the overhead is still very, very low. At least for the asynchronous method. For the synchronous method, we have a little bit higher overhead, but it's still between 2 and 3%, which is quite low. And then we estimated the recovery and how much time consuming is the recovery, or yeah, because when you do the recovery, you have to redistribute the particles in the correct way. And that is more or less fast depending on how you did the checkpoint in the first place. So I don't want to get into the details here, but if you're interested, please go and look in the paper. So again, if we come back to the example, what do we need to do here in order to make it elastic recovery? So you have to define your data set, and that you want to say this is the global data set. Okay, this is not really exactly the syntax that you will use, but I just want to give you a hint of more or less what is that you need to add. And then you add this subset, and you say, okay, I have this grid here, which is part of a global data set. And the global data set has 2 dimensions, and I am using these particular dimensions locally, and I want you to aggregate this into the checkpoint file. Now, again, this is not exactly the syntax, but I just want to give you a hint of more or less how does this look. And everything else is the same. Just by doing that in a regular application, you will be able to do elastic recovery. Now, just to finish, I want to go over more or less what the impact we have seen that FTI had in the last few years. And so just very quickly, there are several European projects that have worked with FTI. So we have Mont Blanc 2, Mont Blanc 2020, Deepest, Legato, EXA2PRO-EoCoE, and the e-processor project that is going to start in a few months. And so because of that, there is a certain number of partners that are starting to use this library and are starting to experiment. For instance, Atos integrated FTI, as part of their software stack, and they did some quite clever work on some of the systems they proposed, because they had this configuration where they had multiple compute nodes with multiple SSDs, which is very, very good for FTI. So you can checkpoint, you can use multi-level checkpointing, but in the middle, they had this router that they are able to reconfigure dynamically. And so this is very useful, because then when you have one of the nodes failing, you can reconfigure this router in order for another node to access what it was in this SSD. And so this is extremely useful. So Atos take advantage of FTI to showcase this hardware architecture that they have developed. We also noticed that Astron, which is the Netherlands radio telescope laboratory, is using FTI for the image domain grading. Please don't ask me what is image domain grading. I don't know. But I would say probably something with processing the large images that they get from their telescope. I'm just guessing here. But we're very happy that they are testing this. I think they're part of the Deepest project. So I guess it makes sense they are working with this. At BSc, for example, we integrated FTI into the ALIA code. I think Edouard already presented ALIA for turbine simulations. And it's already integrated into the master branch and being tested continuously. We also have Huawei interested on FTI, and is interested in testing on their new hardware, because again, you want to take advantage of your hardware in the best possible way. And when you have libraries that do this kind of complex, usage of different storage systems or encoding techniques, then it's really good opportunity to take advantage of the hardware. Now, just to say that Veloce library was funded by the Department of Energy of the United States at Argonne National Laboratory, uses the same interface as FTI. And this makes sense because, in a sense, Veloce is a fork of FTI. I know this because I wrote part of the proposal for Veloce when I was still at Argonne. So at the time the Veloce proposal was being written, I was just about to leave from Argonne to BSc. So I was part of that process. So we use the same interface, so meaning that what you do with FTI would be very easily applicable to Veloce if someday you have to use Veloce. And also, we did some quite recent work. It's a collaboration with Lawrence Livermore Laboratory, in which we integrate FTI with MPI Reinit. MPI Reinit is a proposal to have MPI fault tolerance. So again, if you're interested, please go and look at the paper. It still has not been presented. It's going to be presented in a couple of months in CCGRID 2021. But yeah, again, if you want to take a look, don't hesitate to contact me, and we can send you the paper. And I think it's quite interesting because it's kind of a co-design between MPI fault tolerance and the checkpoint and multi-level checkpointing. So and we managed to fit this in such a way that we take advantage of the knowledge that we have on one side and the other side in order to make this in a very, very optimal fashion. So just to summarize, multi-level checkpointing is quite important, and because it offers you a trade-off between reliability and performance. And it's very good to have asynchronous checkpointing now that you have systems with tens of cores in every compute node, and in many cases you don't even use those. So it's good to have some way to utilize those, and fault tolerance is one of those options. In particular, when you have GPU systems, I mean heterogeneous systems with GPUs, that is a very nice feature to have. It's important to have also transparent checkpointing on systems with GPUs. You don't want to, having to make all the effort to know where is my data set, is in the device memory, is in the host, what data movement I have to do, and then I have to move it to the SSD, and then I have to move it to the file system. So this is just kind of annoying sometimes. So we do all that for you transparently. We offer multiple I/O formats, as I explained, and one of those is actually having in mind that sometimes you can use checkpointing for other than fault tolerance, also for visualization, post-processing, so on and so on. We have implemented differential checkpointing to reduce the amount of storage that checkpoints take. And we also propose elastic recovery for malleable applications that can take advantage of this feature. Just if you want to see all the references, just take a screenshot of this and you have all the papers here. If not, you can ask me for the slides or send me an email. So one last thing is all this work that I just presented was not done only by me. This is a bunch of people working very hard. So you can see all the acknowledgements here about all the people that has been working in this library. So thank you to them. And yeah, thank you very much for your attention. And I will be ready to have questions if you have. Thank you.
Thank you, Leonardo, for the very interesting presentation. Any questions? Okay, then I would like to ask you something. So you mentioned in the beginning the importance of selecting a proper checkpointing frequency, which means that too frequent checkpoints and a lot of overhead, too rare checkpoints mean that we'll have to re-execute a lot in case of failure. So I wonder, are there any tools that help application developers to estimate the optimal, let's say, checkpointing frequency? I mean, how often they need to checkpoint, or even how to efficiently set these L1, L2, L3, and L4 values in the configuration file, or this is left entirely to application developers, since they are expected to know their applications?
Yes. So yeah, very important question. Many people don't know about this. There are several works that have been done for computing the optimal checkpoint interval. And so the parameters that you need to plug in this equation are two. One is the mean time between failures of your system. And the second one is how much time does it take to take a checkpoint for your application in that file system. So basically, mean time between failure and checkpoint cost. With those two parameters, you can plug this into an equation. We call it the Young equation because Young produced this paper quite some years ago. And then with that, basically the solution is something like a square root of 2 times MTBF multiplied by the checkpoint cost. That is more or less the short version of how to compute the checkpoint interval. Then there's a second work that was done by John Daly from Oak Ridge National Lab, in which he computed an even more optimal version of this equation to really optimize the checkpoint interval in the best way. Now, those two works were given when we were assuming only one checkpoint interval because we only had one checkpoint level. Now, since we have implemented multi-level checkpointing, then this, of course, changes quite a little bit. So for that, we actually produced this paper that was published in Super-Computing in 2014. It's optimizations of a multi-level checkpointing model with a certain execution scales. So in this, we look exactly at this problem, is how should I tune these checkpoint intervals for the different levels in order to have the optimal, the minimum waste for my application and for my executions. And the parameters that you have to plug are more or less the same as the ones for single level, but of course for multi-level. So you have to plug the mean time between failures of your system and the cost for each one of these levels that you have. In this case, we applied for FTI, so with 4 different levels, but you can apply it for any other library like SCR that only has 3 levels of checkpointing, and the results will be, the question is the same. So yeah, if you're interested in that, those works already exist, and you just have to look at the paper, and that would be the way you go through those optimal checkpoint interval.
Mm-hmm. Thank you very much. Any other question? Okay, so thank you again, Leonardo.
Thank you.
So this concludes the first day of the workshop. Many thanks to all presenters and participants. So see you tomorrow at the hands-on sessions that start at 9 o'clock in the morning. Thank you all very much for joining.
Thank you.
Goodbye.
May I just one word, please? Don't forget to install all the things that you need to install before the hands-on for tomorrow. It was said many times, but it would be really a waste to spend half an hour or an hour tomorrow before we can start the hands-on. So please do that this evening so that tomorrow we can start the hands-on, because we really have a tight schedule. Sorry, thank you, bye.
Thank you very much, goodbye.
Something else, if I can. I will put the presentation on the website. So far there is only one, but I will try to put all of them if the lecturers are okay.
Sure.
Thank you very much.
Thank you.
Thank you. Thank you.